Good day, grade 12 learners. Welcome to today's Physical Sciences lesson. My name is Dimpo Rampora, and this lesson is brought to you by the Northern Cape Department of Education in collaboration with Phakama Research and Development. Today's lesson is going to be looking at the knowledge area, chemical change, and we are going to be looking at the topic under rate and extension of reaction, but specifically we are going to be zooming into rate of reaction, and this is normally question 5 in your previous question papers. All right, let us get straight to the lesson objectives. So by the end of this lesson, this is what you should be able to know. You should be able to define the reaction rate as the change in concentration of the reactants or products per unit time. You also need to be able to calculate the reaction rate from the given data for reactants using either the mass, or you can be given the number of moles, or you can be given the concentration. So this is the basic equation for rate. However, as I said, that the examiner can give you either the examiner can expect you rather to calculate the rate using either the mass, the number of moles, or even concentration, right? Now you should be able to calculate the average rate, okay, as if you are given the number of moles, that is how you are going to use it. And then if you are given the concentration, that is how you're going to use it. And please notice that here I've included a negative sign over here. You would only indicate a negative sign when you are calculating the rate of reaction for the reactants. Why? Because the reactants decreases as the new products are being formed, okay? Because the products are being formed, that's why the reactants are decreasing, and that's why we put a negative. And every time when you calculate, your average rate must always be positive. All right, you also need to be able to calculate the rate of the reaction from a given data from the product, right? I said you should be able to calculate for the reactants. Now you also should be able to calculate for the product. And also you use the very same equations, but if you can note here, there is no negative sign because you are calculating the rate of the product. Why? Because the products are increasing as the reactants are being used up, okay? The products are increasing because the new products are being formed. That's why we have a positive value. And remember that when you calculate the average rate or the rate of the reaction, the answer must always be a positive. All right. You also need to be able to list the factors that are affecting the rate of the chemical reaction. You also need to be able to explain in terms of the collusion theory how various factors affect the rate of reaction. You also should be able to answer questions and interpret the data, okay, in terms of the table or in terms of the given graphs on different experimental techniques for measuring the rate of the given reaction. All right. You also should be able to define the term positive catalyst, and you also need to be able to interpret the graphs of distribution of molecular energies in terms of the number of particles against the kinetic energy, or what we also known as the Maxwell-Boltzmann distribution curve. To do what? To explain how a catalyst, a temperature or concentration is being affected. All right, so you need to be able to do all of that. All right, so in order for you to be able to do all of that, we need to go back to your grade 10 and 11 and see what is it that you already know in terms of this chapter, or rather, where does this chapter come from? Okay, in grade 11 and in grade 10, you should know, especially in grade 11, how to define exothermic and endothermic reaction. Remember, this was part of chemical change in grade 11. You should also know how to define the heat of the reaction, which is also known as change in enthalpy. You also should know by now how to classify with reasons why reactions are exothermic or endothermic. You also should state that the change in enthalpy is greater than 0, which means that it will be positive for an endothermic reaction, and the change in enthalpy will be less than 0 for an exothermic reaction. You also should know by now how to draw or interpret fully labeled sketch graphs of potential energy versus the cost of reaction of a catalyzed or uncatalyzed endothermic as well as exothermic reactions. You also should know from grade 10 how to state the kinetic molecular theory, okay? And you also should know from grade 10 and part of grade 11, the bond energy as well as the bond length, the differences between the bond energy and the bond length. And you also should know about the activation energy as well as the activation complex. You should be able to differentiate the two by now. You also should know how to use stoichiometry calculations to solve problems. In grade 10, you looked at the mole. In grade 11, you looked at limiting and accessory agent. So you need that all that knowledge in order for us to do well in this chapter. All right. Now that we've looked at what is it that you are supposed to know in terms of the prior knowledge, let us test if you know what we're saying you should know. All right. Let us quickly look at our baseline activity. It says to us, the following reaction between ammonia and oxygen take place in a closed system at a constant pressure and temperature. As you can see, we are given the reaction over there. We have ammonia reacting with oxygen. We have nitrogen oxide as well as water as our product. Then we are given a reaction graph over there. All right, we are given the cost of reaction as our x-axis, and we are given the potential energy as our y-axis. And you should know by now, by just looking at the shape of the graph, you should know if you are dealing with an exothermic reaction or if you are dealing with an endothermic reaction. But let us quickly go to our baseline activities so that we can see if we still remember some of the work. Now, 1.1 says to us, define the term activation energy. Now, activation energy, remember, it is the minimum energy required for a reaction to take place. All right, I hope you still remember that from your grade 11. Now, if we look at here, the symbol EA over here represents our activation energy, which is the minimum energy that was needed for this reaction to occur. All right, now let's look at 1.2 quickly. It says, give a reason why this reaction is exothermic. This reaction, from what we are seeing, is an exothermic reaction because from the graph we can see that the energy of the reactants over here is more than the energy of the product. Okay, so the reason why this is an exothermic reaction, it is because the energy of the reactant is more than the energy of the product, or you can say because the change in enthalpy is less than 0. But for you to be able to say that is because you would have done your calculations already. All right, let's quickly move on to 1.3. It says to us, calculate the heat of the reaction. This is where I'm getting now. Now we are going to prove that this is actually an exothermic reaction. How do we calculate heat of the reaction? Remember, we use the formula change in enthalpy is equals to energy of the product. Okay, it's the energy of the product minus the energy of the reactant. Okay, it's a reactant over there. So how do I calculate that? That is my change in enthalpy over there. That is the energy of my reactant, and that is the energy of my product. I just go to the values over here so that I can see what must I substitute over there. So how much is the energy of my product? The energy of my product is 183.3 minus, okay, the energy of the reactant I have over here is 400. And when you quickly punch that into the calculator, you should get a negative value, which is negative 216.7 kilojoules per mole. All right, kilojoules per mole. Right, this is an indication that the negative value indicates, remember, that the reaction is indeed exothermic. Why? Because our change in enthalpy is less than 0. I hope we still remember this from grade 11. And the reverse reaction for this reaction will be endothermic. Why endothermic? Because that our product will become our reactants, and our reactants over here will become our product. Then we will say the energy of the reactants is less than the energy of the product. All right, I hope you still remember all of that. Let's quickly move on to 1.4. It says, redraw the graph and indicate with a dotted line the effect of a catalyst on an activation energy. Right, now we have to redraw the graph. All right, so I'm not going to redraw the graph with you. However, I am going to show you how you are supposed to do it. All right, I'm going to just use the graph that I already have over here just to show you how to do it. You still have the same graph, but you are going to include your dotted lines over there, and then they will still show you the effect of what? Of a catalyst. Remember, when you add a catalyst, what it does is it lowers your activation energy. So as you can see, the activation energy is lowered from over there to here to here to there. All right, so remember that the effect of the catalyst is just to lower the activation energy, and by lowering the activation energy, and the rate of reaction will be what? Will be faster. All right, I hope we guys together, rather, we are still understanding, and we are remembering all of this that we have learned in grade 11. All right, let's quickly move on to the next question that we should know by now. Right, the next question says to us, the reaction above is the first step in the manufacturing of an acid. All right, which reaction? The reaction that we saw earlier. This acid consists of 1.59% of hydrogen and 22.2% of nitrogen, and we also have 76.2% of oxygen. And our question says, determine the empirical formula of the acid. All right, remember I said you need to remember how to do stoichiometry calculations, which is something that you've learned in grade 11. All right, so what is the first thing that you are going to do over here? As you have seen here, the first thing that you are going to do is to take the percentages. You are going to convert them to masses. Okay, the percentages, you are going to convert them to masses. If you convert that to mass, that will be a 1.59 grams, and then you take that percentage, will be 22.2 grams, and this one will be 76.2 grams. Okay, so you just take the percentage and convert it to grams. Once you are done doing that, the next thing you are going to do is to calculate the number of moles, because you are given the mass. Okay, so over here I'm given the mass of what? Of hydrogen. So here I've already calculated for you the number of moles of hydrogen. There I have it. I'm given the mass. We use the formula N is equals to M over molar mass. Then under the mass we have the 1.59, which is the mass that I've converted from the percentage. Then we are going to divide it by 1, because the molar mass of hydrogen in the periodic table, you just go straight to the periodic table, you go look at what is the molar mass of hydrogen. You will see that the mass number for hydrogen, or the molar mass, is what? Is 1. Then you just punch that into your calculator. You should get that 1.59 mole. And then from there, the next thing you're going to do is to calculate the number of moles of nitrogen. Again, nitrogen, remember we were given the 22.2%. When we convert it to grams, it is going to give us the 22.2 grams. So again, you still use the formula. Number of moles is equals to M over molar mass. Then under the mass, you're going to substitute that mass that we are given, which is 22.4. Then you go straight to the periodic table. You check what is the mass number, or the molar mass of nitrogen. Then you are going to get that as 14. Then you quickly go to your calculator, you punch into the calculator, you should get that 1.5857, all right, moles. And then the last one that you are going to calculate will be the number of moles of oxygen, and then yet again you take that 76.2% and then you convert it into mass, and then you'll get that 76.2 grams. All right, then what you do is you check into the periodic table. You still use the formula N is equals to M over molar mass. You go to the periodic table, you check what is the mass, or the molar mass of oxygen. You should get 16 as it appears on the periodic table. Then you punch in your calculator, you should get that 4.625 moles. Now it doesn't end there. What do? You are going to take you're going to divide with the smallest number of moles. That is the next step. You divide with the smallest number of moles. You have the number of moles of hydrogen. There you have it is 1,59. The number of moles of nitrogen. There you have it as 1,58. And the number of moles of oxygen. There you have it as 4,625. Then between these three values, you then check which one is my lowest number. The lowest number over here is 1,5857. Then you are going to divide everything with 1,5857 rather. Then you divide everything there. When you punch into the calculator, there you will get 1, there you get 1, there you get 3. And then that will tell you the molar, the empirical formula rather of the acid that was used. All right, hydrogen is 1, so there's no need for you to put the 1 there. Nitrogen is 1, there's no need for you to put a 1 there. And then oxygen is 3. And that is how we calculate our empirical formula. I hope you still remember this from grade 11, and this was also done in grade 10. Right, guys, thank you so much for looking at the prior knowledge activity with me. I'm quickly going to jump into the terminology that you need to familiarize yourself with in order for you to understand rates of reaction. So you already did the prior knowledge that activity or the baseline activity with me. You now know what is expected of you as we move forward. All right, let's look at the following terminology that you need to know. You should know how to define the rate of reaction as the change in concentration of the reactants or products per unit time. All right, that is the definition for the rate of reaction. And then another definition that you must know is the collision theory. It is a model that explains reaction rate as a result of particles colliding with a certain minimum energy to form the product. All right, and then the next one is going to be the catalyst. In a catalyst, we are going to be looking at the substance that increases the rate of reaction without itself undergoing a permanent change, and it does that by lowering the activation energy. All right, then we also have what we call the activation complex. It is an unstable transition state from the reactants to the products. Okay, you have seen in the previous graph that we looked at, we had the activation energy, we know what is the change in enthalpy, we know where the products are, we know where the reactants are. And then the next definition that you must know is the activation energy, which is the minimum energy needed for a reaction to take place. We've already spoken about this. This you should know from grade 11. Heat of reaction, you should also know it from grade 11 as the energy absorbed or released in a chemical reaction. Because if the energy is absorbed, then we are saying that is an endothermic reaction. And if the energy is released, then that will be an exothermic reaction. And we see that by looking at the value of change in enthalpy, or which is the heat of reaction. If the heat of reaction is less than 0, then the reaction is exothermic. If the change in enthalpy is greater than 0, then the reaction is endothermic. Exothermic reaction are reactions that releases energy, and the endothermic reactions are reactions that absorb the energy. I hope you guys still remember some of the definitions that you did in grade 11. All right, now let us look at the concept rate of reaction. What is it that you must know when you prepare yourself for your exams? One, you must know everything that has to do with the collision theory, because when we speak rate of reaction, we always refer to the collision theory. You also need to know the factors that are affecting the rate of reaction. Which factors are affecting the rate of reaction? And then you also should know about the Maxwell-Boltzmann distribution curve. All right, this is going to help you when you look at the different graphs that we are going to be looking at as we are looking at the factors that are affecting the rate of reaction. Then we are also going to be looking at the graph interpretations, as I've already mentioned, for the different factors that are affecting the rate of reaction. And as you have seen, we have started with some stoichiometric calculations that you need to make sure that you know before we can start this chapter. All right, so everything that you have done in grade 10 and 11, as you can see, it forms part of this lesson. Now, in order for a reaction to take place, we must remember that in a reaction, we have reactants and products. So in order for the products to form, the reactants need to react with each other, but in order for them to react with each other, they need energy, and they need the minimum amount of energy that is required for them to start reacting. So once that minimum amount of energy has taken place, which is the activation energy, then the particles need to start colliding between the reactants. And when they collide, they must collide with the correct orientation in order for products to be formed. That is where we come to the collision theory. What is it that you need to know in terms of the collision theory? There are 3 conditions that you must know as a grade 12 learner doing this chapter. 1, you must know that the reacting particles, which are the atoms, the molecules, the ions that you find in the reactants, they must do what? They must collide, but they don't just collide. They need to collide effectively with one another in order for them to react. All right. So in order for a reaction to take place, the particles need to collide. The atoms need to collide, the molecules need to collide, but they need to collide effectively for a reaction to take place. The reacting particles must collide not just effectively, but they also need to have the minimum energy that is equals to or higher than the activation energy in order to start breaking and forming the bonds, all right, in a chemical reaction. This is everything that you need to know in terms of the collision theory. The reacting particles, they must also collide with the correct orientation, and that leads to the rearrangement of the atoms, and the atoms will then form the products. So in order for the products to be formed, can you see that it is a process? The reacting particles, they need to collide effectively in order for them to react, not just effectively, but they also need to have the minimum energy that is equals to or higher than the activation energy in order for them to start breaking and forming the bonds. When that has happened, the collision needs to happen with the correct orientation in order to rearrange the atoms and in order for the products to do what? To form. All right. Now that we have looked at the collision theory, you need to take this collision theory with you, because when we look at the factors that are affecting the rate of the reaction, we need to be able to apply the collision theory to explain why this factor is affecting the rate of reaction. All right. Now they have the 5 factors that are affecting the rate of reaction. We have increasing concentration. You know, sometimes the examiner can say to you, name 3 factors that affect the rate of reaction. You can't just say concentration. You need to tell us the effect. Is it increasing concentration or decreasing concentration? As you can see, increasing concentration, what does it do to the rate of the reaction? It also increases the rate of reaction. Increasing the surface area of the substance also increases the rate of reaction. All right. Also, increasing the temperature of a certain substance or a certain environment also increases the rate of reaction. All right. Adding a catalyst speeds up a reaction, the rate of reaction, by lowering the activation energy. Remember, we are looking at what makes the rate of reaction to increase or decrease. All right. And then also the nature of the reactant. What does it do? The rate of reaction may differ depending on whether the medium is in an aqueous solution, or it's organic, or is it polar, or is it non-polar? Is it a solid? Is it a liquid? Is it a gas? So the different states of matter in terms of the nature of the reactants, that is what is going to determine if the reaction will be faster or slower. All right. Now remember, the vice versa of what I've just indicated to you also are the factors that will be affecting the rate of the reaction, meaning decreasing the concentration of the reaction would also decrease the rate of reaction. Decreasing the surface area decreases the rate of reaction. Decreasing the temperature also decreases the rate of the reaction. But when we are adding a catalyst, we must always add it. So we can't just say catalyst affects the rate of reaction. What about it? So we must indicate that adding a catalyst speeds up the reaction rate by doing what? By lowering the activation energy, and it creates a different pathway for energy to do what? To pass through. Remember that A catalyst does not form part of the reactant, it does not form part of the product, but it is just there just to make the reaction to be faster. All right. And now that we have looked at the factors that are affecting the rate of the reaction, the next thing that you need to familiarize yourself with as a grade 12 learner as you are revising this chapter today is to look at, don't forget to look at the Maxwell-Boltzmann distribution curve, because this graph is going to assist us when we are interpreting the graphs of temperature, the graphs of concentration. When we are dealing with those different graphs, we should know what is happening or what are the different labels indicating. So I'm going to start with A over here down there so that you remember what A represents. So when you look here over the graph, first of all, what you need to know is that your y-axis will represent the number of particles. Your x-axis will represent the activation energy. Remember, activation energy, the minimum amount of energy needed for the reaction to take place or the needed for the reaction to start, right? So let's look at letter A. What is happening at this time interval, or what is happening to the energy? Here we have fewer particles. As you can see, there are very few particles over here with very low energy. As you can see, that will be low energy. If we were to put values here, would say that 1, 2, 3, 4, 5, 6. You can see that over here, there is low energy with very few particles. Okay, then B, C, and D. These are the most particles. So here you can see the number of particles starts to do what? To increase. But these number of particles, they don't have enough energy. They have a moderate energy or limited amount of energy for them to do what? To react. But as you can see here, I've also indicated something here. Here I said this is the number of particles that are represented by the area under this part of the graph that do not have sufficient energy to react. So over here, we have the number of particles that don't have enough energy to do what? To react. Where do we get the number of particles that have more energy to react? Every time when we see this shaded area over here, just after your activation energy. Remember, the activation energy is the minimum amount of energy that is needed for the reaction to take place. So just after the shaded area here we have the number of particles that have enough energy or high energy to react. All right. And then every time when the examiner asks you, what does the shaded area indicate? The shaded area always indicates the number of particles that have enough energy to do what? To react, because they are just after the activation energy. And remember, the activation energy is the minimum that you need in order for you to react. So if all of these particles, they have not reached the activation energy, therefore they have the minimum amount of energy that is required for the reaction to occur. I hope you guys are still with me with the Boltzmann distribution curve. Now let's look at into details in terms of what happens when we increase the concentration. How do we infuse the collusion theory on increasing concentration, increasing temperature, or even increasing surface area and the other factors? All right. So for now, I want us to look at concentration. What happens when you increase the concentration? First of all, I want us to look at how you must use the collusion theory in order for you to explain how increasing concentration affects the rate of reaction. First of all, you need to indicate to us that increasing concentration will increase the rate of reaction. How? It will increase the number of particles per unit volume. All right, it will increase the number of particles per unit volume because we have increased the concentration, and more particles will have enough kinetic energy that is greater than the activation energy in order for the particles to start to react, and the number of collisions per unit time will start to do what? To increase. And then we then say the rate of the reaction will also increase. You must notice something here on my slides. I have highlighted these 2 points because these 2 points, that is the only thing that is going to be different when you are dealing with using the collusion theory to explain why increasing concentration or increasing temperature affects the rate of reaction. The rest of the other 3 points, 1, 2, 3, these ones are always going to be the same, depending on either you are increasing or decreasing. Obviously, when you are decreasing the concentration, what is going to happen here? You will decrease the number of particles per unit volume. And what will happen to the particles? You will need less particles will have the kinetic energy that is greater than the activation energy, and then the number of collisions per unit time, instead of them increasing, they will do what? They will decrease, and then the rate of reaction is going to decrease. So it's the vice versa. It's actually the opposite of what I'm saying. Now that you know how to use the collision theory as to explain why increasing concentration affect the rate of the reaction, the next thing that I want to quickly remind you is the graph of concentration. Okay, so you still remember this is still the Maxwell distribution curve. You already know what does that E indicate over there. It indicates the EA represents the activation energy, and you already know what does the shaded area indicate. It indicates the number of particles that have enough energy to react. Anything before the activation energy, all these particles, they don't have enough energy to do what? To react. So now what you need to look at is that I'm going to name this one C1 and this one C2. Okay, C for concentration for one and the second concentration. Now if you look at let me rather say this is C2 because it says graph 2 so that it goes together, and then I call this one C1 for graph 1. So graph 1 represents the lower concentration, therefore there will be less particles. As you can see from the graph, if I look here and if I had numbers over there and I had numbers over there, if I had 0 here, I had 10, and then I had 20, you can see that the graph that indicates more particles, the graph that shows that there would be more particles that are needed to react is this one is graph number 2, which is C2. All right, C2 will be the one that will be showing a higher concentration. Why are we saying that? Because remember, increasing concentration, you will have more particles that have enough energy to do what? To react. They will have enough kinetic energy that is greater than the activation energy, and that is your activation energy. So over here, these are all the particles that have enough energy or enough kinetic energy that is greater than the activation energy, and that's why they are able to do what? To react. However, you then need to compare which one is the highest when you check the number of particles. So as you can see, graph C, the first graph, if I put a number there will be 10, the second graph over there will be what? Will be 20. That indicates to you that the second graph indicates a higher concentration. And what you must remember is that the two graphs, okay, they are not crossing or touching each other. Why am I saying that? You will see that in the next slide. All right, let's quickly move on to increasing temperature. What happens when you are increasing temperature? Again, remember we said increasing temperature will increase the rate of reaction. But you need to use the collision theory to explain why increasing temperature affects the rate of the reaction. All right, increasing temperature, what will it do? It will increase the average kinetic energy of the particles, and then more particles will have enough energy that is greater than or equals to the activation energy, and more effective collisions per unit time, or the effective collisions per unit time will do what? Will increase, and then we say the rate of reaction will also increase. Remember what I said? I said the last points, these bullet points are always the same. What will be different is what you are increasing, or which factor you are increasing or decreasing. I hope you guys are still with me. Now let's quickly jump onto the graph. Remember I said the concentration versus the concentration graph, okay? It has two graphs, but the two graphs are not crossing. Now look at the temperature graph. It also has two graphs, but the two graphs are crossing. So that's how you are differentiating between the concentration graph as well as the temperature graph. The temperature graph, the two graphs must do what? Must cross each other. Then what are you interested in? You are not interested in the peak of the graph. Remember, you are interested in the activation energy. How many particles? Which one has more particles that are greater or equals to the activation energy? All right, if you look at here, I've already said this one will indicate low temperature, and this graph over here, if I call this T1, will represent low temperature, and T2 will represent high temperature. Why? Because if we put values, let's look at T1. T1 is the green one over here. Then look at the number of particles for for the T2. As you can see, T2 has the highest number of particles that are that have enough energy to do what? To react, as compared to T1. T1 has minimum. If I put values here, that will be 0. Let's say that is 10, that is 20, that would be 30 over there. This will be 40. As you can see, if we look at the graph, we really interpret it correctly. You can see that the graph, which is T2, is the one that has the highest number. It represents the number of particles that have more energy that will do what? Will react. Because remember, we are interested in the shaded area. The shaded area, remember, it indicates the number of particles that are needed to do, that have enough energy to do what? To react. I hope you guys can see the difference between the concentration graph as well as the temperature graph. All right. Now that we are still looking at that, let's quickly move on to adding a catalyst. Remember, we said adding a catalyst does what? Increases the rate of the reaction, or it will make the rate of the reaction faster. Why? Because as you add a catalyst, the catalyst does what? Decreases the activation energy. Why? Because it provides an alternative route for a chemical reaction to take place. So it actually creates a shortcut for energy or for particles to do what? To pass through. All right. That's why we are saying it provides an alternative route. And then the next point will say more particles will now have enough energy to form an activation complex, and then more effective collisions per unit time. All right. And then the rate of the reaction will do what? Will increase. Guys, I hope you can see how we are using the collision theory to explain why different factors affect the rate of reaction. All right. Remember, adding a catalyst, what does it do? It creates another pathway, an alternative route for what? For chemical reaction to occur, or for the number of particles to pass through, or for energy to do what? To also take the shortcut. All right, I hope we are still together there. Now let's quickly look at the graph of adding a catalyst. Guys, as you can see, what we are interested in here, when we look at the adding a catalyst graph, we are interested in the activation energy. You check, if I had 0 here, 1, let's say that is 2, 3, 4, 5, 6, 7, 8. Okay, then you check between activation at 6 and the activation at 7, which one represents a lower activation? The one that represents a lower activation is the one where the catalyst has been added. I don't know if it makes sense what I'm saying. So the one that has the lowest activation energy is the one that will be a path route for the catalyst, because the catalyst has created an alternative route for energy, or for chemical reaction rather, to take place. All right. And then we call this activation energy there a newly catalyzed activation energy. All right. Because the activation energy, rather than adding a catalyst, decreases the activation energy. Between the two activation energies that you have over here, which one is the lowest? The lowest one is the one that shows the catalyzed route. Okay, again, that will be particles that don't have enough energy to react, and you also refer to the shaded area. The shaded area will always indicate the number of particles that have enough energy to do what? To react. I hope you can see the difference between the 3 graphs that we have done so far. What is important is the shaded area. You look at the shaded area, you see how many, which one indicates which one has more particles. As you can see, this part is only small, but when you compare all of that, this one is bigger. That's why we say the catalyzed route is the one that is going to make the rate of reaction to be faster. All right, guys, let's quickly look at another way in which the examiner could give you a graph of a catalyst. All right, the explanations are still the same, but what I'm interested in is the graph. Okay, it must start over there at 0. And then what is happening here, guys? This is an exothermic reaction. How do I know that this is an exothermic reaction? The energy of the reactant is more than the energy of the product. Okay, that is the first thing that you need to see. The next thing that you're going to see 2 lines that indicate 2 activation energies. Okay, the 2 activation energy. So the shortest one with the shortest or the less activation energy is the one that will represent a catalyst. So the red color over here is the one that has an activation energy with a catalyst, because what has it done? It has created another way in which a chemical reaction can take place, but instead of you requiring more energy, you'll require less energy. All right, so it lowers the activation energy in order for the reaction to take place. The reactants and the products, they will still remain the same. So this is another way in which the examiner can show you the different graphs. All right, now that we have looked at the graphs, the next factor rather that we are going to be looking at is surface area or state of division. So when we speak surface area or state of division, we are always referring to granules versus powder, or a solid versus powder. All right, so here, as you can see, I have a large chunk here, and then here I have small pieces of chunks, and over there I have powder. So what is important for you to remember is that the one with a granules or the chunks, as you can see, it doesn't occupy. So if we were to look from this point of view, you will see that that is the only space that the chunk is doing what the chunk is doing, what is occupying, and that is the surface area of the chunk. But if you break down the chunk into smaller pieces, you can see that the surface area has done what? Has increased. And if you break these ones even further to make them powder, you will see that the powder takes the larger space of the particles. That indicates that as you increase the surface area, which is the space at which the substance is occupying, all right, that is the surface area or the state of division. That space, as you increase the surface area, the rate of reaction will be faster, all right? So increasing the surface area of a reactant, what does it do? Increasing surface area of a reactant results in more reaction sites, okay? What do we mean about reaction sites? Reaction sites, we mean the specific sites on the molecules at which the reaction will occur. So there's all the specific sites over there at which the reaction is going to occur has been increased. That's why we are saying increasing the surface area, we are increasing the surface area, we are increasing rather the reaction sites. Okay, then what does that do? It increases the number of reaction sites, will increase, and the frequency of the total collisions. And then what happens? More effective collisions per unit time will occur, and they will increase the rate of the reaction, or the rate of the reaction will be faster. So if you are given an activity where you have to compare, the examiner asks you, they are giving you granules, they've given you a powder, you must remember that the powder is an increase in the surface area, and the granules or the solid or the chunks that you'll be given would be a decrease in surface area. So as you increase the surface area, the rate of the reaction will be faster. I hope you guys still remember all of this. This is just the revision. We are just touching and going. And lastly, we said the nature of the reactant depends on whether that particular reactant is a solid, or is it a liquid, or is it a gas? Is it polar? Is it non-polar? Is it ionic? Does it form bonds? Is it covalently bonded, or does it form ions? You know, so all of that depends on the nature of the reactants, and the nature of reactants will then determine if the reaction is going to be faster or slower. So the medium at which the reaction occurs, as I've said, the liquid, gas, solid, you know, all the different states of matter, as well as the properties of the reactants. What are the different properties of the reactants? Does that mean that this particular substance reacts faster when it gets heat? Does it react faster when it gets cold? Does it react faster when it's a liquid, when it's a gas, when it's polar, or when it's non-polar? So the properties of the reactants are also important. So the rate of the reaction may differ depending on whether the medium is aqueous, I've already indicated that, and polar, non-polar, liquid, solid, or gas. But the reaction rate in which the ionic and the polar solutions are involved, it will always take place faster. So which type of reactant is going to make the reaction faster? The ones that are ionic and the ones that are polar. Okay, in polar solutions, then the rate of reaction will be faster. I hope you guys are still with me. Now let us quickly take an air break because we deserve it and we need to digest what we have just revised now. And when we come back, we will look at an activity. Thank you.